Welcome everybody to today's seminar. Today's speaker is Claudia Landi, and she will talk to us about barcodes for the topological analysis of gradient-like vector fields. Please take it away.
Thank you, Hannah, for the introduction, and many thanks to all the AATRN crew, because it's really an honor and a great pleasure to be talking at this seminar today. As you said, the topic today is barcodes for the topological analysis of gradient-like vector fields. This is a joint work with Clemens Banwart, a PhD student at the University of Modena and Reggio Emilia in Italy, same institution where I'm based. As the title says, we would like to propose an approach to summarize the topological properties of a vector field using barcodes. Okay, now it is not working. The change of page now. Okay, so I'm starting with some background, but not because I expect you are not acquainted with this, but just because I'd like to be sure we are thinking about, we are on the same page, because there are different flavors of persistence, and in this talk, we want, in this work, we wanted to generalize this persistence pipeline. The data is not a sample of the manifold M. We don't want to study the shape of the manifold M, but we want to study summarize the function defined on this manifold with values in R. For example, this is the data. The function is the data. It can be a measurement on the manifold. And the usual way of doing this is to take sub-level sets of this function so that one gets a parametrized topological space, meaning that we have a parameter t, and varying this parameter t, we can obtain the various sub-level sets. Now, so this can also be thought as a functor from the reals to the category of topological spaces. And usually this is called a filtration, because when t is smaller or equal than s, then the corresponding sublevel set under t is contained into the one under s. Then one can apply the homology functor, usually with the coefficients in a field, and then one gets what is usually called a persistence module, and we can also see as a functor from the reals again to the vector spaces for a fixed degree of homology, and so we can also consider this as a parametrized vector space. So again, we have a parameter that varies, that's t, and correspondingly we have a vector space associated. So here the notation is that the sublevel set is MT, and we compute the homology of that sublevel set. And from this there is a final step, which is summarizing this topological information captured by the homology using a barcode. And this is due to the fact that one can decompose the parametrized vector space into indecomposables that have a very simple support. The support is that of an interval, which corresponds to the fact that we have a birth of homological features and a death of homological features. So BD are the endpoints of these intervals where we have a birth and death of homological features for a fixed degree homology. Now, we don't want to do this again. What we would like to do is to do this for a vector field. So where a function can be also thought of as a scalar field, and we want to do this for a vector field, but we immediately run into problems because we don't know how to set up a filtration associated to a vector field. So this is just to illustrate pictorially. This is the manifold M, this is the function f, and for each value t we have mt, and then we can apply homology, and we have these barcodes that are intervals. But yes, this is not easy to understand how to do something similar for a vector field. So but this is our goal, to obtain a barcode for a vector field. And the barcode is an invariant. An invariant of what? For scalar fields, the barcode is an invariant of the function of the scalar field up to reparametrizations of the manifold, meaning that two functions f and g for which there exists a self-homeomorphism of the manifold, a self-homeomorphism H of the manifold such that this equality is satisfied, will give the same, these two functions, if they are in such a relationship, then they will give the same barcode. So the barcode captures the properties of the functions up to reparametrization of the manifold, up to composition with the self-homeomorphism that preserves the level sets. But so in this sense, they are invariants of the function, but they are also invariants up to functor isomorphisms of the persistence module. So our goal for vector fields is not only to build any functor, because we could consider a vector field as a function in a sense, and so we could apply usual persistence for multiple scalar fields, for example, but we want to build a barcode that is also a topological invariant for the vector field. What does it mean? Vector fields are topologically equivalent to vector fields V and V prime are topologically equivalent if and only if there is a self-homeomorphism of the manifold that maps orbits of the first vector field to orbits of the second vector fields. And so we want also this. So we want to build barcodes and functors that are invariant up to this topological equivalence. But this topological equivalence alone is only qualitative. We want also something quantitative, and so we ask for an isometric topological equivalence. But by this we mean that we want this homeomorphism to preserve the distances among singularities. This is, we assume we are on a Riemannian manifold, and we want the topological equivalence also to take into account how far away singularities are from each other. And again, we want to build a barcode which is invariant for these functors up to isomorphism. So a double sense of invariance. The sense of invariance, topological invariant, but also algebraic in the sense of the compositions. And the desirable properties that a barcode should enjoy are easy easiness of computability, stability, and a counterpart for when I'm talking about vector fields, I mean smooth vector fields, but we would like also a counterpart for combinatorial vector fields. So how can we achieve this? Well, again, looking at the usual persistence pipeline for scalar fields, for functions, many recent papers have suggested not to jump to homology in this pipeline, but to consider chain complexes. So instead of parametrized vector spaces, to consider parametrized chain complexes. And from this, the study of these chain complexes can still give us exactly the same barcode. Of course, in this case, all the degrees are considered at once, and so we also have the barcodes in all different degrees. But still, this doesn't solve the problem we have with vector fields about how to filter the manifold using the vector field. However, it is considering chain complexes is already useful, because chain complexes are something that are shared both by functions and vector fields. Now, when I talk about a vector field, I'm talking about a gradient-like vector field, so a vector field without closed orbits. This is because, and also Morse-Smale, because it is for Morse-Smale vector fields without closed orbits that it is possible to associate to the vector field a chain complex exactly as it is possible for functions. The chain complex has the vector spaces that are generated by the zeros of or singularities of the vector fields in the corresponding degree. So in degree K, we have the space generated by singularities of index K. So for example, on a surface, minima for a function and sinks for a vector field generate the degree 0. Vector space saddles generate the degree 1, and the sources or maxima generate the degree 2. And in between, we have boundary maps that are defined by counting, for example, modulo 2, the number of flows connecting two singularities, two zeros of the vector field. So chain complexes is a commonality for functions and vector field. The Morse complex is something that they have in common, and we wanted to use this, but still we don't know how to filter such a chain complex. So what can we do? Well, the idea is that another way of thinking about persistence is that it drives the simplification of a function. So we can think, instead of filtering the manifold, we can start simplifying the vector field in much the same way one pairing birth and deaths of sublevel sets of a function can simplify the function. And so, for example, we can start simplifying this pair of points, a minimum and a saddle, and this simplifies the vector field like that. And then we can also pair these 2 points in the vector field and simplify them from the vector field, cancel them together and simplify it until we are left with something that cannot be cancelled, because it gives the essential homology of the manifold. But doing this simplification at vector field level is easy for on manifolds of dimension 1, dimension 2, but in general it is not easy or even possible. So what we want to do is to do these simplifications at the algebraic level of the chain complex. So instead of having a sequence of vector fields that gets simplified, we start with the Morse complex of the given vector field, and then we start simplifying pairs of generators of this chain complex. And this is the idea. So if we, the type of object we want to associate to a vector field is what we call a tame epimorphic parametrized chain complex. What does it mean? We have a functor that for each value t, real value t between 0 and infinity, associates to it a chain complex. We call it, and so for this reason it is a parametrized chain complex. We call it epimorphic when all the internal maps that we have for two values of the parameters, between two values of the parameter, they are surjective, which is exactly, which is different than what we have for filtration. For filtration, usually these internal maps are monomorphisms. And then we require tameness. Tameness is a technical requirement that says that basically there are only finitely many instances where things are going to happen, and so it is a discretization of the time. And we denote this category of tame epimorphic parametrized chain complexes by this symbol, and this is the category we want to study, and because later we will associate to each vector field of Morse-Smale gradient-like vector field an object in this category. So first thing that we observed is that each element can be written as, in this category, can be written as a finite direct sum of indecomposables of this form. Vertically, we have chain complexes. You can see this diagram. Each vertical column is a chain complex, meaning that the composition of two maps gives a 0, while the parameter varies horizontally, and we have that the horizontal maps are epimorphisms, are surjective. Now, in this, the composables are such that they always start with something that has a 0, is non-trivial, but is zero homology. And it remains like so. It remains like this for a bit, and then at some point it becomes it starts having a homology. Homology becomes non-trivial, and then it is trivial again, possibly because everything is 0. So it is like an interval, but it is thick because it is in 2 degrees, n and n minus 1. And so and so there are 3 relevant times in this interval. The starting time, 0, then the time where homology starts, and then the time where homology ends. Okay, and so this type of indecomposable is described by 3 numbers, basically. One number is the dimension where we are, if we are in between degree n and n minus 1. Then we have the number s that tells us when homology starts, and then time t, which is the death of homology. And objects here can be decomposed in this way. And so this type of interval, we called it a tagged interval, in the sense that it is like a normal interval, but it has a specific element, a tag in the middle of it. And what's in particular, if we among these indecomposables, those for which have if X has a constant homology, then the indecomposables are only of two types. They are like this, from 0 and S is equal to T, and this means that the rest is a 0, or they are like this. So 0 is equal to S, and then they keep going forever until infinity. And this is the essential part of the homology. And for when we have these objects, we can also define distances for these objects. We have the usual interleaving distance. We have also bottleneck distance, and we can prove an isometry theorem analogous to the one for persistence modules of one parameter persistence. And also in this case, the interleaving distance, in the case with constant homology, we can prove it in the case of with constant homology, the interleaving distance between two parametrized tame epimorphic parametrized chain complexes is equal to the bottleneck distance between these tagged intervals. And so this is a similarity already. But how can we create such parametrized chain complexes, starting from a chain complex which is not parametrized? So if we start from a chain complex, and we want to parameterize it, turning it into a tame epimorphic parametrized chain complex, then what we need is the following. We need to fix a basis for each vector space in the chain complex, and we also need to fix weights for to associate two pairs of generators of the chain complex. So we have a weight W AB. Whenever A is a basis of in degree K, is a basis element in degree K, and B is a basis element in degree K minus 1. And these weights, we want them to be positive and finite. In particular, the based chain complex, a weighted based chain complex, will be called generic if these weights are pairwise different. So we are in a generic situation when there are no two equal weights. And so these generic weighted based chain complexes will be the set of them will be denoted by this. And now we want to construct a tame epimorphic parametrized chain complex given any weighted based chain complex, which is generic. And we have a procedure. Basically, the procedure is start with, so y is what we want to construct. We start setting it equal to 0. Then each time we find a pair AB such that B belongs to the boundary of A, and the weight is the smallest possible among all the weights that we have. Then we will, what can we do if we find such a pair of basis elements? Then we can say that we have an interval. We can add to y an interval with a tagged interval 0tt, where t is the value of the weight, and n in this case is the degree of the generator A. And in case we cannot find such a pair, then this means that we have already simplified all the boundaries, and so we can go to the end. Once we add such an interval to y, then we can update the original chain complex C by quotienting away this disk generated by A and the boundary of A. We need to update the basis and the weights accordingly, and we repeat until we remain without any non-trivial boundary. At that point, we just add as many intervals. So this is an interval like this, from 0 to t. Now here we add all the intervals like this. And so basically what we are doing, we are quotienting out at each step, we are quotienting out an object of this type, and this can be done easily, even algorithmically. For example, if we are in Z2, because it amounts to find a non-zero column. So we take the total boundary of the chain complex, considered with respect to the fixed basis, which look for a non-zero column. And while this non-zero column exists, then we can consider the time of corresponding to the minimal weight between two elements, such that Bi is in the boundary of Bj. We can append that tagged interval and its degree to the barcode, and then this corresponds, a simplification corresponds to a change of basis that can be done simply by a Gaussian operation on the rows. We add the ith row to the kth row, and whenever K and I have both a non-trivial element in column J, and then we shrink the matrix by deleting all the row I and the row J, the column I and the column J. So the matrix becomes smaller. And we repeat this until there is a non-zero column. When there are no more non-zero columns, then we can simply append these intervals to the barcode. And then we output the barcode. So it is easily computable because operations are very easy. And stability. What about stability? Whenever we can find a bijection between two bases that induces an isomorphism of chain complexes and preserves the order of the weights, then we can define it in a natural way, a distance, such that the interleaving distance of the constructed tame epimorphic parametrized chain complexes is smaller or equal than the distance between the two chain complexes. And this is what we want to do for use for vector fields, because now we want to start from a vector field. We want to start from a vector field. We are assuming that it is gradient-like, it is a Morse-Smale, and also that it is in general position. By this, we mean that the distances between its singular points are pairwise pairwise distinct, and we can associate to such a vector field a tame epimorphic parametrized chain complexes. How? We first consider its Morse complex, and then using this construction here, once we have a Morse complex, we have also a basis for it, and we can have weights, and for this we can obtain a tame epimorphic parametrized chain complex. So what are the weights to be used in this, construction? The weight between, because here the generators of the chain complexes are the singular points, so it is simply the distance between the singular points. And so we have a way of associating with each vector field, plus we need to be given a Riemannian metric on the manifold to define the distance between points. Then we can associate to it, using this construction, a tame epimorphic parametrized chain complex. And as we saw, the tame epimorphic parametrized chain complexes have an interleaving distance which is equal to a bottleneck distance, and have a barcode that can be computed by the previous algorithm. The previous stability result, this one, that was at level of chain complexes, weight-based chain complexes, this stability result induces this property that this function that takes a vector field to its tame epimorphic parametrized chain complex is a continuous map. What does it mean? Practically, it means that if we take a vector field V prime in a small enough neighborhood, in a small neighborhood of the vector field V, then we are sure that this map maps V prime to a tame epimorphic parametrized chain complex, which is close to that of V. And so we have a continuity. This map is continuous. The last property we are interested in is the following one. Usually we don't work with the smooth vector fields. Usually people work with combinatorial vector fields. And so how can we use all of this in this case? Well, it can be used without any restriction, because also in the case of a combinatorial gradient-like vector field, we can define the corresponding when it is, we can define the corresponding Morse complex. In this case, the basis to be used is the basis given by the critical cells of this discrete vector field. And what we need is are the weights. How to define the weights? Well, for example, if this simplicial complex is triangulates a manifold, a Riemannian manifold, then the weights can be given by the distance. The weight of a pair of critical cells sigma 2 can be set to be equal to the distance between the barycenters of these cells. So there is an easy way also so we can easily define a weighted and based chain complex, also starting from a combinatorial gradient-like vector field. And as soon as we have a weighted and based chain complex, we know that we can transform it into a tame epimorphic parametrized chain complex. So also in the case of combinatorial gradient-like vector fields, we can map any the vector field into a tame epimorphic parametrized chain complex, which can then be decomposed, and we can consider its barcode of tagged intervals. Last observation is the following one. What is the relationship between the smooth and the combinatorial vector fields? Now we have this result that we call the combinatorial approximation theorem that tells us this. If you take a smooth vector field, we are always assuming that it is a gradient-like, it is a Morse-Smale, and it is generic. We have a triangulation of this vector field in the sense that we have a triangulation of a manifold, of the manifold M, and we have a combinatorial vector field on the simplicial complex triangulating the manifold that correspond bijectively to the smooth vector field, in the sense that there is a bijection between critical cells of capital V and zeros of the smooth vector field small v, and also the flows connecting to critical cells are in bijection to the flows connecting to singularities of small v. Then it is possible to define the barycentric subdivision of the vector field using a construction by Zhukova. While the triangulation I described briefly is due to Gallet. And what we can show is that the tame epimorphic parametrized chain complex of the smooth vector field can be approximated arbitrarily well up to any arbitrarily small epsilon by the tame epimorphic parametrized chain complex of a discrete vector field. It is sufficient to take a large enough barycentric subdivision of the discrete vector field in order to obtain the desired approximation. Of course, in measuring the distance between these two objects, we use the interleaving distance. And so this result says that with this construction, one can pass from the smooth. We are sure that we can pass from the smooth to the combinatorial and discrete case with arbitrarily good precision. So all of this is reported in this preprint that you can find our archive, and but we would still like to add something. It is easy to see that the scalar field can also be described in this way. So we can build also a barcode for a scalar field, a tagged barcode for a scalar field. That's not complicated. It will not be the same as the barcode for a filtration, because our bars all start at the same, if I have a picture here, they all start at 0. Okay, it's too back. So, okay, they all start at 0. So It will not be the same, but it will be related. The point is that we used we used a lot the genericity condition, which means that the weights need to be pairwise different. And usually when we work with usual persistence of scalar fields, we don't ask this property, and it is always possible to break the ties if two simplices, for example, enter at the same time. So now, presently, we are working to obtain this for scalar fields. We would like we are trying to understand if we can, for scalar fields, we can abandon the genericity condition, whereas we think that we need to maintain it for vector fields anyway. But later, we would like to extend this study to consider the case of vector fields with closed orbits. And of course, it would be very nice, after one has understood the scalar fields and vector fields, to extend this to tensor fields. The problems here are how to define the chain complex, because we always need to start from a chain complex. In the long term, exactly because we need the genericity condition, in the long term, we would like to study, to try to understand if it is possible to consider also bifurcations. So, and that's the reason why understanding scalar fields without genericity condition is important to us. And so I thank you very much for your attention.
Thank you, Claudia, for the very nice talk. Before we go to questions, I would like to ask everybody to unmute themselves and clap for the speaker. All right, now it's time for questions. So please, if you have a question, just raise your hand or unmute themselves. I see Bay already has a question. Please take it away, Bay.
Yes. Thank you, Claudia. Really good talk. I have a question. When you measure the distances between critical points or singularities, I assume you are using intrinsic distances along the one skeleton, right? It's not Euclidean distances.
No, exactly. The manifold, in the smooth case, we assume that it's a Riemannian manifold, and so we are using the geodesic distance. And
okay.
in the discrete,
and then second question.
In the discrete case, here so also here I think we are thinking of this simplicial complex as embedded somewhere, but we are measuring the distance on the manifold, not in the ambient space. In this theorem, however, because we are triangulating a manifold, actually we are mapping all the simplicial complex to the Riemannian manifold, and so we are the distance is that of the manifold.
Mm-hmm. Yeah. So my second question is, does your stability result, which appear to be stability with respect to this new sort of what you'd call TEP category, does that imply some form of stability of the Morse complex?
Of this, sorry?
So you have a stability result if you go to that slide.
Yeah. Okay. This is a sort of stability result, but is it this one? Even if in this one it is local stability. So because we are only considering generic So we are considering a subset of the set of all vector field. So we are, so if you think of this as the space of vector fields, we are removing all of them that are not Morse-Smale and which are not in general position. We take a vector field here, and what we say is that we can always take a neighborhood. So
they have to be in their own strata in your analysis
yeah,
here.
exactly. In this theorem, it is like that. In this theorem, it is like that. Exactly.
Okay, yeah.
That's why, yeah, exactly. It is local stability. Yeah.
Okay, thank you.
Ines had a question. Please go ahead.
Yeah, thank you very much for the talk, Claudia. If you could go back maybe to the structure theorem slide, I had some questions about it. Maybe it's way back. Yeah, here. Yeah, so you said that all the intervals start at 0, like all the first coordinate of all the intervals starts at 0. And I was wondering, that is because of the epimorphism condition that you're imposing, right? So I guess my question is, why do you want that condition to hold, or how important it is to have epimorphisms? Like, why are you motivated to take that?
I mean, there are papers, but they don't try to say anything about vector fields, where opposed to this, chain complexes are filtered in the sense that the maps are monomorphisms instead of epimorphisms. And so they can start with 0, and then usually it is reversed, like they start with 0, and then at some point something is homology is born, and at some point homology is killed. And these, in that case, these are include in monomorphisms.
Yeah, and in that case, you always have as the last coordinate.
In this case, one finds a usual taking the homology of this, because here the homology becomes 0. One gets taking homology, one gets the usual intervals. Okay, but for vector fields, okay, it would be very nice, but we have not find, no idea came to our mind how to do that. So we are rather doing the opposite. We start with the complete chain complex, the one that usually one finds at the end of the filtration. We start with that. And we start quotienting out things that we think we are simplifying. And so they are epimorphisms because they are quotients. And so they needed to start like this.
Yeah. It reminds me of like relative homology, like this, like relative chains, complexes, and stuff like that. And also, I guess my second question, if I may, is you're saying in the theorem that S and T can either be S0, T plus infinity, or they have to be equal?
Yes, because and decomposables are like this. If it has a constant homology, not all, of course, not only, but if X has constant homology, so it is this. And in our construction, we construct things in such a way, our X always has constant homology.
I see. Thank you.
Exactly for that reason, because we start off with a chain complex and we start quotienting out things of this type until we can. And when there are no longer things of this type, it means that we remain only with things of this type.
Yeah, I see. Thank you.
You're welcome.
Are there any more questions for Claudia? Bay has another question, I see.
I can keep asking questions if there's nobody asking more questions. But I just want to ask one more. Just looking at this picture, if I am using your way of the weighted sort of chain complexes with the chosen basis, in this case of vector field, is there like have a, I think the slide 3 or 4, you have a picture that's showing how you would like to build that chain complex through simplification. So I'm wondering, can we somehow have an intuitive notion? Yeah, exactly this picture.
Yeah.
Is it true, and you can correct me, this is fairly intuitive. Is it true that if I go from the first picture to the second picture, where I simplify a pair of minimum and saddle, that I destroyed a homology class? Is this what's being captured, or the barcode is captured something more than this?
And no homology class is destroyed because this pair doesn't give any homology. Exactly because the pair okay. So we simplify, but the homology doesn't change because this pair has a trivial homology itself. It is like when you simplify, when you simplify in a function small this, the homology is not changing. So I don't know what homology you are talking of, but the homology of the manifold remains the same. So the manifold maybe is this.
Yeah, I guess what I'm trying to do is to create an intuitive understanding of when you apply your theory to a sequence of sort of vector field simplifications. When do I see sort of non-trivial signal? That's where I'm trying to get at. You know, under what condition I will start seeing something
non-trivial. But so, for example, if the distance between these 2 points is 1, the distance between these 2 points is 2, and then we have 3 and maybe 4. So the first one that is cancelled is this pair. So we start, so we get at this is time, between time 0 and time 1, we have a barcode like this. This is degree 0 and this is degree 1. This means that here I have F, and here I have F, and the same is, whereas here it is 0, 0. Here it is constant FF, and then it becomes 0. Then at time, this is time 1. At time 2, where I simplify this pair, this means that I am adding another bar to the barcode between 0 and 2. But at this time is in a higher degree. It is between degree 1 and degree 2. And again, I have F. So in terms of chain complexes, each time I have F. It remains like this until it becomes 0, 0 at time 1. Again, here it is F, and it continues. FF between time 0 and time 2, until it becomes at time 2, 0, 0. So I imagine them as things like this. And this is the signal. So even if the homology is trivial of this stuff, it still gives a signal that something is happening to the vector field. It's a feature of the vector field.
Yeah, okay, makes sense. Thank you.
You're welcome.
Are there any more questions for Claudia? Okay, I would have one question. I mean, I understand that you mainly work with the it's very long names, tame epimorphic parametrized chain complexes that have constant homology, and you've got this stability result for them. But did you also consider, you know, similar stability result when you drop off the constant homology?
Well, we have no result in that. We have no results in that case. And we have not even tried to find them because by construction we don't get that case. But I think it becomes more difficult. Already for the case of monomorphic chain complexes, it is not easy to understand stuff. For example, I think that Facundo Memoli and Ling Zhu have studied this, the question of stability for filtered chain complex of a Vietoris-Rips complex. And but I think it is still not well. I think it is not well understood for chain complexes. So we have not studied for epimorphic unless they are of constant homology, which yeah, maybe it's the easy case.
Well, to me it sounded complicated enough. But basically you are using these chain complexes, sort of you take a vector field, right? And then you have this whole construction which produces this this chain complex that has constant homology, and then you work with this. But can you, and the vector field, so the TEP chain complexes that you produce from the vector fields, which is the construction you talked about almost at the end, they always have constant homology, right?
Exactly, by construction.
Yeah.
Actually, Clemens came up with a different construction. I presented this one because I find it simpler, but also the other one is interesting. But again, it's always with constant homology, because the idea is basically the same. You start with a chain complex and you simplify, and simplifying means quotienting by these sort of things until one remains with something like this, which has so maybe this is a minimum and this is a maximum. So one remains with something in degree 2 and something in degree 0 that this was on a sphere, of course, that lasts forever, and in between the map is a 0. So they are two bars that, well, of course, in between there is a 1, but anyway, and so also the other construction, instead of taking as a time where to hand a bar exactly the weights are summed to each other, so that but otherwise Yeah, we do not have a construction that doesn't give a constant homology, which is maybe our luck, because this means we can apply results that are easier for constant homology. But yes, we couldn't give an interpretation of the others. So in terms of what one gets from a vector field, I wouldn't know how to interpret this.
Can you imagine how you would, I mean, sort of, you've got these vector fields, and from that you've got this pipeline that gives you these TEP chain complexes. Can you imagine how much you can generalize the notion of vector fields in order to still get the chain complexes? Or did you ever think about generalizing because that's where you started, right? You started with considering sort of scalar vector fields, which were functions, and then you generalized to vector fields. Did you think about generalizing even further?
Already generalizing to vector fields that have closed orbits is not meaning that it's a periodic. It's still something that we can, if it exists, it cannot be perturbed away. So, but we don't know how to build a chain complex to start with. So in our construction, we always need to start with a chain complex. So if we already have a mathematical construction that comes from, I don't know where, but it already exists that associates to some mathematical object a chain complex, then we can apply our procedure. And that's the case of functions, Morse functions, Morse-Smale functions, and the case of Morse-Smale vector fields, which are gradient-like. But already Morse-Smale vector fields that are not gradient-like, and so they also present this, so we don't know how to deal with them.
Okay, so one just needs to provide you with an object plus a
exactly.
All right, great. Thank you very much.
I have a small question maybe about this point. Thank you for a very nice talk, by the way. So just that I understand, speaking about methods for producing chain complexes, right, when you are giving these vector fields, am I correct in my understanding that your last part of the talk, when you can produce somehow a triangulation of your manifold with a discrete Morse vector field in the sense of Foreman, that the main way you do this is by some work of Gallais, I think. Is this the tool you're using for that?
Not to produce it. So the chain complex, both for the smooth case and the discrete case. Okay, in the smooth case, the chain complex exists. It is the Morse complex. And if we are given a Foreman discrete gradient-like vector field, also in that case, the Morse complex exists. That's something that is known.
Yes, but then you talk about discretization.
Yeah, now Gallais proved that given, and I think that also Benedetti has a work about this, is they studied how to connect the two theories, and in particular Gallais proved that for any smooth vector gradient-like Morse-Smale vector field, there exists a triangulation such that a triangulation of the manifold and a gradient-like discrete vector field on that on the simplicial complex given that triangulation, such that there is this bijection. So
right.
This is I hope I'm repeating correctly the results by Gallais.
Yes, my question was, so gradient-like is also in the hypothesis of this, right? So
Yes,
just
yes,
trying to
yes.
understand
I
whether
think,
there is...
sorry for the notation, I think is this G.
Okay, thank you.
Yeah, it needs to be gradient-like because also Gallet is working in that, and also Benedetti, they are working all in that case. The
Thanks.
only work where that we are aware of that considers the case of periodic orbits is that by Jürgen Jost and Martier Eddy. And they apply Frank's trick, but we are still looking into that.
Okay. Thank you.
Okay, we're a little bit over time. So if there are no more questions, thank you, Claudia, again, and I will stop the recording now.
Thank you very much for your attention.